Hey guys, welcome to day 17. The mole continued. So yesterday I kind of introduced to you the idea of the mole. It's kind of the chemistry equivalent of the dozen. So if you're wanting to deal with one amount of substance, you deal with a mole of a substance. Now, one mole is an extremely large amount of particles, 600 to billion trillion atoms, molecules, or formula units. So it's impractical to count that high. But more often than not, what we're going to do is we're going to take the mass of a sample, say in grams, we can convert it into moles, or maybe we know the volume of a substance and we can convert that into moles. So you're not actually counting. The mole is really just a way of counting without actually counting. It's more of a mathematical way of getting to a number. So we kind of know what a mole is. Avogadro's number represents the number of particles in a mole. But today we need to realize that different elements have different weights. For example, hydrogen is a very light element, and 1 mole of hydrogen is going to weigh less than, say, for example, 1 mole of gold. Gold is a very heavy atom, so 1 mole of gold is going to be considerably heavier. Kind of like saying if I had a mole of grapes versus a mole of watermelons. A mole of grapes would be much less weight, and a mole of watermelons would be much more weight. Now, if you're counting, you may have the same number, okay? But in weight, they're going to have different weights. So how can we convert from grams into moles? And the way that we're going to do that is with the molar mass. Now, going back in history, we already kind of know what atomic mass is, and I've given you the definition here. We talked about atomic mass way back in chapter 4. Basically, it's the average weight of an atom based on its abundance of isotopes in nature. Remember when we did the M&M lab and we had to count and weigh and average all their weights? Same idea here. So the atomic mass is what we actually see on the periodic table. And I've given you some examples, like for hydrogen. So the number at the top of the box in this case is going to be the atomic number, and that's your number of protons. Now, the number that we're concerned with is the atomic weight. Now, in chapter 4, we express this in atomic mass units. But in this chapter, we're going to do something a little bit different with it. So let's go back up here and kind of define what is a molar mass. Okay, the molar mass is simply how much 1 mole of substance weighs. Now, the units are pretty important to you. The units are going to be the gram per mole. Now, if you kind of go back and think about atomic mass is usually measured in AMUs, which stands for atomic mass units. It's simpler than it looks. All you're going to do is unit swap. So you're going to replace AMU with grams per mole. Okay, let me give you a few examples here. All right, so the first example is going to be carbon. Okay, now carbon is the reference isotope. So carbon 12 has exactly 6 protons and 6 neutrons, and 1 mole of carbon 12 will weigh exactly 12 grams. So what we do is we look to the periodic table, and for carbon, carbon has an atomic mass of 12.011. And this number at the bottom is the atomic weight, okay? So the average mass of a carbon atom is about 12 AMUs. Now, this isn't very useful to us, so what we're going to do is we're going to basically swap out the AMU and we're going to replace it with a gram per mole, and it becomes a conversion factor. Basically, what this is saying is that 1 mole of carbon atoms is equal to 12.001 grams. Now, for the sake of example, all of my answers have been rounded to the nearest tenth. When we do your homework problems here in a few minutes, I'll talk a little bit more about rounding. But basically, we've just taken that AMU and we've said that 1 mole of carbon is equal to 12 grams. And because you guys already have a copy of the periodic table, it should be pretty easy to pretty much look up the molar mass of any element. It's as simple as looking at the periodic table. All right, so let's look at my next example. My next example is hydrogen. And if you find hydrogen on the periodic table, its atomic weight is 1.008, okay? And so what that is saying is that 1 mole of hydrogen atoms has a mass of 1.008 grams, okay? But we have a problem here because hydrogen is on that list of elements that likes to form in pairs. Um, Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine like to form in pairs. So when we're considering a mole of hydrogen, we have to consider its chemical formula as well. So if we had 1 mole of hydrogen atoms, it would weigh 1.008 grams. But if we had 1 mole of hydrogen molecules, it's going to be double, which would be 2.016 grams per mole. So 1 mole of diatomic hydrogen is going to weigh twice as much as a mole of monoatomic hydrogen. So when you guys are doing some of these problems tonight, you must consider the elements that forms in pairs. And tomorrow we'll talk a little bit more about compounds, and we'll get into that a little bit more detail. Now, assuming that you have a periodic table, all you're doing is swapping out atomic weight and you're replacing it with grams per mole. So now, this is important. We said that the atomic mass of carbon was 12 grams per mole. We said that the atomic or the molecular molar mass of monoatomic hydrogen was 1 gram per mole. So if we had 1 gram of hydrogen atoms, we would have exactly the same amount of atoms as if we had 12 grams of carbon. So what we're doing here is, rather than counting individual carbon or hydrogen atoms, we're just comparing weights. So basically, a carbon atom is 12 times heavier than a hydrogen atom, okay? So let's go ahead and take a look at your homework down here, okay? All right, a couple definitions. So for number 3, you're going to calculate the molar mass of the following substances. Use the periodic table and round these to the nearest hundredth. So I know in the notes I went to the nearest tenth. I would like you guys to go to the nearest hundredth. So let's go ahead and start with neon. Now I need to get my copy of the periodic table handy. So what I'm going to do is I'm going to find neon in the periodic table, and its atomic number 10, but its atomic weight is 20.1797, okay? And I kind of asked you in the instructions, I wanted you to round to 2 decimal places to the nearest tenth. So this would be in AMUs, but when you report your answer, I want you to report it to 2 decimal places, and I want you to basically report it not in AMUs, but in grams per mole, okay? So the molar mass of neon is 20.18 grams per mole. And really what this is saying is that 1 mole of neon gas is equal to 20 grams, okay? And this is going to be a conversion factor that we use in the next few days, okay? Very important concept. Let's do another one. All right, let's look at diatomic hydrogen. Now, if I find oxygen on the P table, it's 15.9994, and we would assume that's in AMUs. But we're not going to report our answers in AMUs. We're going to report them in grams per moles. And also, we want to round our answer to 2 decimal places. So if I do that, if a 9 is followed by a 9, we round it up to a 10. And in doing so, 15.9994 is actually going to round up to 16.00. But what we did is we forgot to consider the 2. So we're going to multiply this factor by 2, and what we're left with is the molar mass of diatomic hydrogen, which is twice that of monoatomic hydrogen, is going to be 32 grams for every 1 mole. So 1 mole of diatomic oxygen is equal to 32 grams in weight, okay? So don't forget to consider the diatomic elements. All right, let's do another one. Let's do ozone. So we just kind of did one with diatomic oxygen. So now what we're going to do is we're going to take 3 times this 15.9994. And when we do that, we're actually going to round it to 2 decimal places, and what we're left with is 48 grams per mole. So triatomic oxygen, ozone, is more heavy for a mole than is diatomic oxygen, okay? So really just consider what the weight on the periodic table is, and then round it to 2 decimal places. All right, last one is going to be manganese, and manganese is not to be confused with magnesium. Manganese has an atomic weight of 54.938044. And remember, you guys are going to 2 decimal places, so we're going to call it 54.94 grams per mole. All right, guys, so I think molar mass is a pretty simple concept. I'm not saying that Moles are an easy concept, but at least this concept of molar mass is relatively easy. Next time we get together, we will be converting from grams into moles or from moles into grams. And in order to do that, you need to understand dimensional analysis, and you also need to understand this idea of molar mass. So molar mass is a conversion factor that allows us to go back and forth between grams and moles. All right, guys, if you have any questions, you can email me directly. Don't hesitate to leave a comment on Google Classroom. I miss you guys. I love you guys. I'll talk to you soon.